Welcome back. I'm Momar Lone, and in our last episode, we explored how to transform text into basic numerical representations. Today, we're diving into the cutting edge of word representations, the sophisticated techniques that are powering the most advanced language understanding systems in the world. Imagine having a mathematical model so precise that it can capture not just the meaning of words, but their relationships, their contexts, and even their subtle emotional connotations. This isn't science fiction, it's the reality of modern word representations. Let's start with a thought experiment. Consider these three words: king, queen, and palace. How would you describe their relationships? As humans, we intuitively understand their connections, but today we'll learn how machines can understand these relationships through advanced mathematical representations. Evolution of word embeddings. Before we dive into the most advanced techniques, let's understand how word representations have evolved. The journey. 1. One-hot encoding. Each word is a sparse vector, no relationship information, simple but limited. 2. Count-based methods, co-occurrence matrices, statistical patterns, better but still sparse. 3. Word 2 vague revolution, dense vectors learned from context, semantic relationships. 4. Modern contextual embeddings, dynamic representations, context-aware, state-of-the-art performance. Let's explore each advancement and understand what makes modern approaches so powerful. Word 2 vague deep dive. Word 2 vague represented a quantum leap in how we represent words. Let's understand why it's so powerful. 2 key architectures. 1. Skip RAM predicts context from target word, better for rare words, more comprehensive relationships. 2. Continuous bag of words, CBOW predicts target from context, faster training, better for frequent words. Let's see it in action. Consider this sentence: the quick brown fox jumps over the lazy dog. For the word fox, word 2 vague looks at previous words, quick, brown following words, jumps, over. The magic happens in the neural network. Input layer, one hot encoded word, hidden layer, dense representation, output layer, context prediction. This creates vectors where similar words cluster together, relationships are preserved, analogies can be computed, semantic meaning emerges. The famous example: king, man plus woman, queen. This works because the vectors capture gender relationships, royal status, human attributes. Global vectors. While word 2 vague learns from local context windows, GloV takes a global approach. Key innovations. 1. Global co-occurrence matrix counts word pairs across corpus, captures broader patterns, preserves global statistics. 2. Weighted factorization balances rare and common words, efficient training, robust representations. 3. Explicit relationship modeling, direct optimization of ratios, captures fine-grained relationships, better analogy performance. Let's analyze this approach. Matrix X, word co-occurrence counts W, word vectors C, context vectors B, bias terms. The optimization objective: minimize difference between dot product and log co-occurrence. Weight function prevents rare words from being ignored. Symmetric context windows capture bidirectional relationships. Fast text, subword information. Fast text introduced a crucial innovation: handling words as bags of character n-grams. Key features. 1. Subword units, character n-grams, morphological awareness, better handling of rare words. 2. Compositional representations, words as sum of subwords, shared components, efficient storage. Example: word, faster subwords. Benefits: handles unknown words, captures morphology, reduces vocabulary size. Improved rare word representation enables cross-lingual transfer applications, morphologically rich languages, technical vocabulary, social media, text, multilingual models. Contextual embeddings. Now we enter the era of contextual embeddings, where words get different representations based on their context. Key technologies. 1. BERT, bidirectional encoder representations from transformers, bidirectional context, deep transformer architecture, pre-training and fine-tuning. 2. GPT, generative pre-trained transformer autoregressive modeling, large-scale training, powerful generation. 3. Roberta, XLNet, and beyond, improved training, larger datasets, better architectures. Let's see how context changes meaning. I'm going to the bank, financial institution or riverbank. The crane lifted the container, construction equipment or bird. Contextual embeddings capture word sense, disambiguation, syntactic roles, semantic relationships, pragmatic meaning. Advanced techniques. Let's explore some cutting-edge approaches in word representation. 1. Multitask learning, shared representations, multiple objectives, transfer learning, better generalization. 2. Cross-lingual embeddings, language agnostic spaces, translation capabilities, universal representations, cultural understanding. 3. Domain-specific embeddings, specialized vocabulary, technical relationships, domain knowledge, custom applications. 4. Multimodal embeddings, text-image alignment, audio-text representation, cross-modal understanding, rich semantic spaces. Visualization and analysis. Understanding these complex representations requires sophisticated visualization techniques. 1. Dimensionality reduction, TSNE, UMAP, PCA, interactive visualization. 2. Relationship analysis, cosine similarity, Euclidean distance analogy testing, clustering analysis. 3. Evaluation metrics, word similarity, analogy, accuracy, downstream performance, intrinsic evaluation. Practical applications. These advanced representations enable powerful applications. 1. Machine translation, cross-lingual understanding, context preservation, style transfer, cultural adaptation. 2. Question answering, deep comprehension, context awareness, precise answers, natural interaction. 3. Text generation, coherent writing, style matching, creative content, technical documentation. 4. Semantic search, meaning-based retrieval, query understanding, relevant results, user intent. Future directions. The field continues to evolve rapidly. 1. Efficient representations, model compression, quantization, sparse attention, hardware optimization. 2. Interpretable embeddings, explainable features, semantic dimensions, controlled generation, bias detection. 3. Dynamic adaptation, online learning, continuous updates, domain adaptation, personalization. 4. Ethical considerations, bias mitigation, privacy preservation, fairness metrics, responsible deployment. Implementation guidelines. Success with advanced word representations requires careful consideration. 1. Model selection, task requirements, data availability, computational resources, performance needs. 2. Training strategy, data preparation, hyperparameter tuning, validation approach, iteration cycles. 3. Deployment considerations, scalability, maintenance, updates, monitoring. 4. Quality assurance, testing protocols, performance metrics, error analysis, continuous improvement. Closing. As we conclude our exploration of advanced word representations, remember, context is crucial, relationships matter, evolution continues, applications expand, ethics guide development. In our next episode, we'll dive into supervised learning techniques for NLP tasks. Until then, try this exploration. 1. Compare different embedding models. 2. Visualize word relationships. 3. Test analogy performance. 4. Analyze context effects. 5. Consider practical applications. I'm Momar Lone, and thank you for joining me in this deep dive into advanced word representations. Remember, every word carries multiple meanings, and modern NLP can capture them all. Keep exploring, keep analyzing, and I'll see you next time. Stay curious, and keep embedding.